Hello and welcome to the inaugural lecture that we have today, or better, two inaugural lectures that we have today of Per Nowack and Benjamin Schäfer. My name is Michael Beigl. I'm here as Vice Dean for research because Bernhard Beckert, our Dean, cannot come today, unfortunately. So I jumped in for him. It's not my job to say a lot of words about Per and Benjamin, but to hand over immediately to Peter Braesicke and Veit Hagenmeyer, who will introduce both and who know also their work better than I do. And I just say hello, and then I say, let's go to have some drinks at the very end. So the nice things are up to me, the other things are up to the others. So Per Nowack is introduced by Peter Braesicke, and I will ask him to say a few words about him and introduce him.
Yes, so thank you very much. So I wasn't entirely sure what the introduction would be like. So I prepared sort of a little speech that can be anything from 5 to 15 minutes. I'm sort of told reliably I shouldn't make it for too long. And I wasn't speaking that much about the person because Per will introduce himself as well. And I've seen a few slides, so I know what's coming. So I've had a sneak preview. But I also wanted to introduce a little bit the process because I find it very, very amazing how KIT can sometimes work. So basically, Per's professorship is called now Artificial Intelligence in Climate and Environmental Sciences. And I think the obvious thing is how to talk about such a thing that is certainly future technology and also perspective for us at KIT. And I started to think about three simple parts: the genesis, so how does it happen at KIT, the revelation, it works in the end, hallelujah, and then the ascension and the paradise to come. So I just wanted to sort of briefly mention that my first contact with this professorship was the 31st of October 2018. It is not a spelling mistake. I checked it. When I got a phone call shopping at Edeka in the evening from my section or division head, as they are now called, Dr. Ziegan, that there was an opportunity to get a professorship for something with artificial intelligence in Earth and environment. And I should write him by tomorrow, late lunch, something he can use when he is discussing it with Professor Kraft. Which I did. So the day after, I sent sort of a couple of ideas, what I would think those professorships should be doing, at least in our area. And so on the 1st November 2018, I sent off the first draft of the content description of what I would like such a professorship to do. Nothing happened. It was very, very urgent. It had to be done by next day lunch. Nothing happened. But turnaround is slow at KIT, but in the end, something happens. And that's what I call the revelation. So KIT sometimes works on biblical timescales, as we know. And eventually, after having talked many times to Dr. Ziegan, a few times to our Vice President Kraft, and others, on the 2nd November 2021, so I have the dates on my little list here, there was the first meeting of the appointment panel to create the advert. Hallelujah. However, content-wise, nothing had changed. It was still basically the description I sent on the 1st of November 2018 in the early afternoon, which was pretty good. So that advert went out, and we had lots of good applications. I think I'm allowed to say how many there were. There were 34 applications, and we were really pleased with this huge interest we generated in the community. And so when we basically had the first TIFF, it turned out that I unfortunately had to leave the panel because I knew two of the candidates. And obviously one of them was Per, because we obviously met earlier already in Cambridge many years ago. And that's how I now come basically to Per's introduction. So Per did a PhD in Cambridge, and I was lucky enough to be involved in this modeling PhD as well. So I know him from certainly slightly different, more modeling-based, numerical modeling with partial regression-based endeavor. Yes, come in. Still some seats left. Welcome. And so basically, I was then very, very happy to hear that eventually the panel decided to suggest Per for this professorship. And he started in March last year. So, and that's now how we come here. So Per, who was then at UEA, University of East Anglia, doing already sort of something like artificial intelligence and climate sciences, accepted, luckily, this opportunity here to help us in our research field, Earth and Environment, and here at the Department of Informatics with this area of artificial intelligence in the particular application field of our wonderful program, Changing Earth, Sustaining Our Future, in what is now called the Research Center, oder Großforschungsaufgabe, as we say, because that's basically where then the future lies for many of those professorships here. So I think it's really a great opportunity for KIT to have created this network of artificial intelligence professorships, to have now really capable, really cool scientists and researchers on these positions that basically really build a bridge between the informatics department and the different research fields and the different disciplines. And I think it's a really great opportunity also for future-proofing KIT by also adapting a future-proof technology. And so because I talk so much about the future, I brought this little book. I don't know if you know this. The Future Is, and basically when I saw this book the first time, I had two recollections. Orange is the new black. So that would be the one thing if you basically like streaming services, or basically the future is bright, the future is orange. That would be more sort of, when you lived in the UK, you would know that this is sort of a nice slogan by a telecom company. However, that is a collection of stories, and one of the stories actually deals with artificial intelligence, or in Germany, künstliche Intelligenz. And the sort of finale of this little story is that you shouldn't worry too much about the future and have it instead a good night's sleep. And so to remind the candidate of that is something he also should do sometimes, I hand him this book, and basically I hand him sort of the baton now for giving his presentation. And so please welcome Per for his presentation on artificial intelligence for climate science.
Thank you so much, Peter. So that I don't have to hold this all the time, I would try to change. I have to switch this off, yeah. Good, can you hear me all right? Okay, good, great. So just hoping this doesn't drop. So first of all, it's good to see so many known faces, but also new faces. Might be because Benjamin is here, so that more people from the energy sector here are here today. But yeah, it's great to get to know you. And I should apologize. I was on a conference last week, so I brought back a cold. So my voice might just accidentally drop out from time to time, but I hope that's all right. So let's move on to my slides if I can. I think this hasn't caught on it. Okay. Okay, thank you so much, Benjamin, also for trying to jump in. So my topic clearly is AI for climate science, or broadly, my Lehrstuhl is about climate and environmental science, but it's an extremely broad subject. And as such, come on in. And as such, I thought I'd focus today on climate science, or even more specifically, climate change, just because it's a very exciting topic. And I think here in informatics, maybe some of you might want to learn more about it. But Peter already mentioned, he sneaked into the slide and said, I don't really have to repeat what you will say anyway, or take this away from you. So Peter already mentioned, I started here in March last year. So I'm green, red today, not green, as a tenure track professor in this position. But and I'm originally from Germany. So I grew up in Baden-Württemberg, Freiburg im Breisgau, certainly known to many of you. Very beautiful city, and Karlsruhe is obviously very close to that. So I'm very happy to be back here. But beforehand, I spent many years abroad. So I studied at ETH Zurich in Switzerland, interdisciplinary science, which is pretty much perfect setup for what I'm doing now, except in one aspect. So this was physics, chemistry, and computer science. but it didn't include any climate science. So this only I got to know while I was abroad for a year at the University of Cambridge, and I liked it so much that I stayed for the PhD afterwards, just a few months later, to do a PhD in climate modeling, basically. And in the same group, I then went on to do a short postdoc, and then I got a great opportunity in London at Imperial College to follow a junior, or basically lead a junior research group, where the title is already quite suggestive for what I'm doing today, Machine Learning to Advance Climate Science. So this was a 4-year fellowship. Some of you who are familiar with the UK system might know what a fellowship is, but it really offered me a great path into this machine learning artificial intelligence domain. And during that fellowship, 2 years in or so, I got an offer for a permanent lectureship at UEA, so University of East Anglia. And those of you from the climate science domain might know that this is the first institution in the UK to ever do climate change research. So I started this in the 1970s, so now my voice is dropping. 1970s, so I really went back to the roots and really learned a lot about from very long-term climate scientists who really started this discipline. And maybe funny enough, when I went to KIT and everyone told me this was the first faculty of informatics, I felt sort of at home as a result of it. Yeah, but I had a great time at UEA, but also very glad to be back in Germany, and especially in Baden-Württemberg and here at KIT. During that time, I should mention, so I went abroad, basically worked abroad and went abroad further abroad to the US, also for a summer internship at the National Center for Atmospheric Research, which is very well known as one of the eminent institutes in atmospheric science. But how I see based on this experience I have so far, my role here at KIT is bridge building, right? So I'm now at the Faculty of Informatics. My research has always been very method focused, so building new modules, models, more tools for climate and environmental science. So building this bridge is really at the sort of core of my enterprise. And just as an early shout out in my talk, we have an open group seminar series every 4 weeks. And if you are interested in this, I feel the microphone is somewhat loose. If you're interested in this, then do join us. These are meant to be informal seminars, so not formal colloquia where we can discuss recent work involving machine learning in these application domains. So if you're interested in this, then please come and find me or one of my staff members later to get on the right email lists and so on. So as I already mentioned, I won't be able to dive into every possible application today using machine learning in these domains, but just to highlight, if you are interested in this, I put a lot of material online as well on our Lehrstuhl website, so you might find more there. But the basic idea is that I really believe that machine learning can act as an integrator to combine data sources, for example, from observations, from numerical models, from sensor measurements, and so on, in completely novel ways, and can bridge also the gaps between some of those domains within the application domains. And I would just like to give you a few examples how this can work today from my previous research. And now, as I said, many familiar faces here because I've talked to many of you, but clearly not all of you. So here I just listed a few institutes I'm already in touch with concerning collaborations and interesting connections, interesting ideas. But this should not just be about immediate ideas for common research, but also if you're interested in climate change, in learning more about machine learning, then do reach out. And so far, this has been a real pleasure. And clearly, I just hope that this is going to continue over the next few years. It has brought me not just from Campus South here, where I'm mostly based, to Campus North, but even to Campus Alpine in the Alps, our outpost, so to speak. And this was 2 really nice days in the Alps. So overall, I would say KIT is really an enjoyable place to work. So if you're interested, do get in touch. Okay, but let's move to something more climate sciencey. So I basically jumped this, but I thought I'd bring you climate science, especially climate change, in a nutshell. So it might not be a surprise to you that climate change is happening. So if we look at just this map here on the left, this shows annual, sort of smooth 24 months annual temperature changes from 1880 to 2023. What you can basically see is that we are continuously moving with some internal variability, clearly from blue anomalies to yellow, reddish anomalies, right? And this is basically what we all know about, the global warming signal. So if you integrate this globally, you can see here on the right side that global warming is happening. And just here for 2023, that this was a particularly hot year. So the months June to December, globally integrated, were record-breaking by quite some margin. And this is a dramatic signal, but we understand quite well to a certain degree that this is the forced climate change signal, but also a specifically warm year last year due to a strong El Nino event. So if you are a bit into climate science, you might see here this anomaly in the East Pacific highlighting a strong El Nino event, which is known to lead to, also in terms of internal variability, very warm temperatures globally. But there's still some research going on to understand why exactly this gap was so large compared to the previous years. But now these are historical temperature changes, right? So we know this is going on, but the key question now is what happens in the future, right? And for this, it comes down to computer scientists and physical scientists collaborating to build ever better models of the climate system. So we have to represent a number of very complex processes that we think are important for climate. So this includes from melting ice sheets to changing clouds, which I will highlight later on as a key uncertainty factor. So there are multiple processes, a huge number of processes that we have to represent, atmosphere and ocean dynamics as well. This is basically fluid dynamics. And we have to then try to project and also understand from a policy point of view what are possible scenarios that we face in the future. So socioeconomic pathways, because we don't know how the world will change in terms of greenhouse gas emissions, aerosol emissions, and so on, which force the climate and change it. And then we have to put this into a numerical climate model, and this poses immediate challenges, as many of you in the room will know. Often a much more complex numerical grids than are shown here. But the basic idea is that we have to represent these processes and the fluid dynamics and the energy budget on a very high-dimensional, horizontally and vertically resolved numerical grid. So we have to really represent deep into the upper atmosphere, stratosphere, mesospheric scales often, and also deep down into the ocean, the carbon cycle uptake, so the carbon uptake by the deep ocean and energy budget of the oceans. So this is very quickly very computationally expensive. And this is why I'm quite glad to be again here at KIT, because the HORICA system, I will use it not just for machine learning, but also to run these numerical models. And this is something I already highlighted in a few talks here at KIT. So if we have these numerical models, there are certain bottlenecks, right? And sources of uncertainty, which is really the key focus of my research. On the one hand, we have highly expensive processes that we could resolve, but they're just very computationally expensive to solve. So here at KIT, we have, for example, a lot of research going on in atmospheric chemistry, and I will highlight this as an important topic of my own research as well. And then we have subgrid scale processes. So for example, clouds, because these numerical models still have a grid resolution of multiple kilometers typically, so we cannot resolve individual clouds or aerosol microphysics. So we have to parameterize these in some way. And these really lead altogether to uncertainty in future projections of climate change, both in terms of the dynamics and the thermodynamics. And what I truly believe, and why I'm so interested in this particular position here, is in the first place is because I think machine learning is a game changer. It allows us to do things, and we see things happening on a time scale in terms of development that was previously unseen in this domain. So now I mentioned this term uncertainties a few times, and I've already talked to a couple of you here in informatics, had quite interesting discussions about what uncertainties we have to take into account in climate change projections. And I just highlight this here again for a grid location in Central Europe. Because I guess every one of us cares about this to a certain degree. So it's just indicated here by the red square. It's actually not a square because it's 5 degrees in longitude and latitude, and it's somewhat exaggerated because I wanted to make it visible on the map. But let's just look at climate change projections for this grid point, okay? And what you can see here is in black, observations according to the Climatic Research Unit observational data sets where I worked before at the UEA, who publish for long term now an observational record of global climate change. And then on top of this, you see in gray here results of 34 different climate models from the coupled model intercomparison project phase 6. So these are state-of-the-art climate models built by modeling centers around the world. So US, various countries in Europe, Russia, China, Australia, and so on. What you can see is that these different models, they're not expected to match the internal variability historically, right? So these models were run under historical forcing conditions until the year 2014, roughly. You see they don't match the internal variability because these are free-running models with their own internal variability, but they see the same forcing conditions. They broadly follow this trend for this grid point, right? And what we can do with these models, what we can't do in observations, is try to look into the future. So what happens if we kept emitting CO2, have a fossil fuel-driven economy, sort of a high-emission business-as-usual scenario? What you can immediately see is that these 34 different trajectories all point upwards, but that there's a large spread, diverging spread in the projections relative to the temperature in early 20th century. And clearly in models, you can also ask yourself what happened if we try to run a strong mitigation scenario, for example, avoid 2 degrees global warming, which still translates into a larger warming on land surface temperatures, I have to say. And now immediately from this, you can see there's a obvious uncertainty in the case that if you ask yourself, what is the warming by 2050 going to be, that each year can be particularly warm or particularly cold in a model, right? So you have internal variability uncertainty, which makes it difficult to say in advance what a temperature in a particular year might be. But if you look at the statistics of these simulations, like the multi-model mean and the ±2 sigma interval or so, you get immediately an impression that, well, there is a diverging trend between those two scenarios, right? And if you look by the end of the 21st century, 2100 roughly, the one scenario might imply a multi-model mean warming of maybe 6 degrees warming or so, whereas the strong mitigation scenario would probably be closer to 2 or 3 degrees warming. And this is what we refer to as scenario uncertainty. It depends on which path we choose. And then we have, and this is sort of the elephant in the room, model uncertainty. And this is a large part of what my research is about, and where I want to highlight a few applications that even for the same forcing scenario, you can have climate models that warm just by 3 degrees for this grid point or by 10 degrees for this grid point. And that's a huge uncertainty, basically meaning completely different climate risk assessments or worlds, so to speak. And this is what we refer to as model uncertainty. And a lot of my research focuses on how we can use machine learning to combine Earth observations and to evaluate which of these projections are more realistic overall. But before I do this, just a quick look at how climate modeling has evolved over time. So as you can imagine, that as the supercomputers in which we have to run these simulations, so computing power has evolved and scientific knowledge has evolved, these models have gained complexity to full-blown Earth system models. And this also means that we resolve a larger spatial scale now, so vertical resolution, but also higher horizontal resolution and so on. But there are still processes we cannot resolve explicitly. But one component I want to highlight here is atmospheric chemistry, because it's still quite a recent component because it's so computationally expensive. And as Peter already indicated, during my time in Cambridge as a PhD researcher or student, as we said over there, I worked with global climate models and looked into the effects of what happened if we coupled for the first time an atmospheric chemistry module to these sorts of global simulations. What you can see here is a standard first order experiment by climate scientists, where you take this climate model, add a component or leave the component out like it was before, and force it, kick it really hard by a 4 times CO2 increase in the atmosphere. So by doing this, you basically get a radiative forcing, so an energy change similar to sort of the high emission scenario I had on the previous slide, but it happens instantaneously. So you get a very large signal to noise. What you can see is that relative to pre-industrial control simulations, where you don't have any human influences on this model system, that if you included interactive chemistry, so atmospheric chemistry or chemical fields from these interactive chemistry runs, you end up at around 20% difference in warming than if you didn't include this component. So this would be a classic case in climate science where you would say, okay, this is a component we would like to include more consistently in the future in simulations. However, this leads then to the direct dilemma that certainly many processes face, but atmospheric chemistry is a classic example that, including this, slows down models quite significantly. So the simulations I run back then were slowed down by a factor 2 or 3, and if it took me 2 months to run the one simulation, it took 6 months to run another simulation. So that's a significant slowdown. It basically has to do with the transport of chemical tracers and the large chemical system of rate equations that you have to solve at every single time step. So maybe not surprising given what I'm doing today, I then suggested, why could we not get an approximate solution that basically represents these effects in a much more computationally efficient way using machine learning? And the short answer is that a lot of parameterizations like this have been suggested since for this community, but for atmospheric chemistry, I believe it's particularly successful. So we implemented this in the UK Earth system model for the first time, and it's a stable version that we have now running, and it's, as far as I'm aware, the first machine learning parameterization of this kind that we can run stably for long time scales. And we are now incorporating this as part of Eling Ma's PhD project, who is in the audience today, into IconArt. So I'm very excited about this project because it's very close to my heart, clearly, and I'm very excited to carry on this work here at KIT and to build this parameterization for more emission scenarios and so on. Okay, slight sidestep, because I mentioned ozone on the previous slide as one, and you could have seen it in one of the graphs, as one of the key species that we have to model under climate change. You might have heard about ozone in the context of air pollution. So just to give you some environmental science context, there are a lot of forecasting tasks we have to take. So for example, ozone air pollution, you might have heard about it during summer times. Heavy ozone pollution is something that we also see in the Black Forest. And just to highlight some work of my PhD student, he's a PhD student at the University of Cambridge, who I co-supervise, Sebastian Hickman. A recent paper showed that architectures like the temporal fusion transformer can really not just outperform previous machine learning approaches when learning from high dimensional spatial temporal data to forecast ozone pollution multiple days in advance in Europe, but also outperforms even bias-corrected numerical models. Now, this might be still an somewhat unfair beauty contest, but at least for certain chemical species, I certainly see great potential here to use machine learning to create larger ensembles much more quickly than we had previously. But yeah, so this on the environmental science note. So back to climate model uncertainties. So another key aspect of my work has been to address these model uncertainties I mentioned. So we have these huge spreads in climate model projections, regional and global scale, and we basically try to evaluate which of these projections might be more realistic. And one main source of uncertainty that has been known for quite some time is changes in clouds, because clouds play a very important role in the Earth's energy budget, and we know that they are going to change very likely. There are multiple mechanisms that can lead to either clouds having a positive amplifying effect on global warming, or maybe also on the contrary, reducing effect on global warming. And which one of these mechanisms wins out is basically an open question to a certain degree. And now, as part of this work, I've basically developed a new, more generic observational constraint framework, fundamentally in controlling factor analysis, that in novel ways combines, for example, satellite data and model data to derive observational constraints. So what do I mean by this? To use observations to constrain model uncertainty. And the detailed steps of this are clearly beyond the scope of this very short talk here. But the key idea, just to bring this across, is that you learn functions that are climate invariant, so that you can learn from historical data, evaluate on historical data that you can observe, then also look at future projections to use this as a constraining relationship. And this for machine learning means that you have to either find complex ways to linearize your relationships, or for example, use physics-informed machine learning to make this robust. And just to highlight two papers that use this framework, you can see here a constraint I published with a dear colleague of mine, Paolo Ceppi from Imperial College in London, already a few years back, to constrain the global cloud feedback. And here on the right side, during my time already here at KIT, a constraint of on a highly uncertain feedback in the stratosphere. So changes in stratospheric water vapor, which appeared in Nature Geoscience last year. And because it's such an important topic, I've got two excellent postdocs working in this domain. So one of them is Dr. Sarah Wilson-Kemsley, who can't be here today because she's still based at UEA, where she's funded through the ML4 Clouds project, which I lead. And then there's Dr. Moshgan Ami-Amjadi, who's sitting here today, who has joined KIT just a few months ago to work on the stratospheric part of this observational constraint framework. Okay, so I don't want to stretch on model uncertainty for too long, but just because I know there are a lot of technical people in the room as well. So if you're interested in causality, then please do find me, because I'm deeply convinced that if we want to use machine learning to build models in these sorts of domains, we have to go beyond pure correlation frameworks, right? So looking at causal discovery algorithms has therefore been an interest of mine for a few years now. So what happens if we want to build more robust models and maybe combine this with physics-informed machine learning? I see there are a lot of opportunities moving forward. And if you're interested in this, just have a look at a paper I published with a few colleagues in Nature Communications a few years ago, where we basically suggested using causal algorithms for climate model evaluation. So again, with the goal to reduce model uncertainties. So yeah, I don't want to stretch this on for too long before Benjamin takes over and Veit Hagenmeyer, but just one more, because I talked about internal variability uncertainty a lot and model uncertainty, clearly its scenario uncertainty plays a big role too, right? So a good example is different climate forcing agents have different timescales in which they act. Methane, for example, stays in the atmosphere for around 10 years. So a good strategy could be to ask yourself, well, a possible strategy, I'm not sure if it's a good strategy, could be to ask yourself, could we not just mitigate methane emissions much more quickly and CO2 emissions to stay below 2 degrees warming? And these sort of questions, especially on a regional scale and coupled to aerosols, mean that we would like to run these climate models under more policy scenarios than we currently can, right? Because they're so computationally expensive. What we are working on is to use the big data archives we already have from the scenarios to ask ourselves the question, could we not learn a machine learning emulator, basically, of climate models that gets around having to run the Earth system model again and again, and instead, for a variety of different scenarios, can output changes in key climate impact variables like temperature and precipitation. And this work has been ongoing for quite some time, first with a PhD student at Imperial College, Laura Mansfield, and now more recently, when we defined 2 different types of benchmark data sets for this task. Because really, what is the complexity here is to define interesting data sets and do the pre-processing, for example, to define tasks that the machine learning community can take on to learn machine learning models at scale. Because the raw CMIP6 archive is around 30 petabyte, so that's nothing nice to handle just to try something out. So having good problem definitions and benchmark data sets prove to be really valuable here. Okay, I heard it's custom in these Antrittsvorlesungen or Inaugural lectures to briefly talk about teaching. So I've already taught for the first time the module on machine learning and climate and environmental science last winter semester, which consisted of 2 hours of lectures per week and 2 hours of exercise, 2 hours of exercise classes per week, consisting of Jupyter Notebook exercises. And yeah, on popular request, you could say, we are now running a corresponding master seminar, which will be led by Moshkan in the summer semester, and I will run at the same time for the 3rd time now the pro seminar on related topics. And as I said before, if you want to join our open group seminars, then please reach out to us from various institutes. We're always keen to find new interest across different institutes. And then in winter 25-26, it's also planned that I will contribute to the undergraduate teaching as part of Grundlagen der künstlichen Intelligenz. And clearly, I'm also very excited. I'm sure there will be a few undergraduate students here today to always supervise plenty of thesis projects of the excellent KRT students. Okay, good. So if you're interested in this, then please do find us for friendly discussions, hikes, or whatever you might be interested in. We're still quite scattered across different countries and universities, but a core is here at KRT, and we want to make our visitors feel welcome at home or at home here as well when they come. So please do reach out to us if you like and get in touch. And on this, I think I'm already running well out of time now, Benjamin, so I might just hand over. But there are many more topics I could discuss. So urban heat islands, wildfire risks, really long-standing issues and urgent issues we need to tackle. So if you're interested, again, the collaboration invitation is here. And on that note, I will end. And usually I would take questions. I'm not sure if that's a custom in Antrittsvorlesungen, but in the interest of time, I would suggest Veit Hagenmeyer could take over. And we have a discussion later on over food and drinks. Thank you.
Yeah, thanks, Per. Very exciting talk. Also exciting topic and important topic as well. I hand over to Veit immediately in the interest of time, and there's also normally no questions, and better questions come out after a few glasses of champagne, I guess.
So he's always referring to the champagne. So, but I think we're here for the two new professors. Are we? Yeah. So I'm, of course, I'm so well prepared that I have the full CV of Benjamin, who I should present with me. And he just told me that he has all of that on slides. So my plan is gone. Yes, I was not quite sure how to give a laudatio or inaugural speech for you, Benjamin. Benjamin. And so when I asked him what I should say about him, then he said, you could say something you always wanted to tell about me. Yeah. And at the same time, when entering this very lecture hall, I encountered a very bright colleague who told me, that's not so difficult, Veit. Say something nice. And so I can say that the union of these two sets is large. So I can tell you he's really a nice guy. Yeah. A very nice guy. And it's great to have him here. Moreover, he's not only a nice guy, he's a cool guy, because he said, whatever you say, music would be nice. The best would be a rap. Yeah. Please rap it. Not rapid, but rapid. And and I'm not rapid in that. So my problem is that in English, to rap, I don't even know how that works. My children told me you have to make this hand movement. Yeah. And you have to say yo yo. Yeah? So my task is now to say yo yo, and then perhaps spontaneously I would say, I don't know, but something like Benjamin, you're so cool. Yo yo, far away from any fool. Yo yo, you will set the new energy rule. Yo yo, with AI of your Lehrstuhl. Okay, I stop here. Yo, yeah, that's right. So perhaps I'll tell rather how I came to know him. And the point was that in the institute, I'm in. There was work even before I came to the institute, which was called electrical data recording. Yeah, so very bright colleagues set up a kind of measuring device for energy time series. And they collected lots and tons of data together with the SCC. And we have lots of great data, but they were, I'm not saying lying around, there was work on it, but we lacked someone who had a new vision, a new perspective on it. And that was in the time of Göttingen, yeah, and then later on in Dresden, where we somehow came into touch, and you discovered that data treasure, yeah, and he made wonderful things out of it, including Nature publication and so on. He will later on speak about it. And then, yeah, some years later, you were already in London, as far as I remember. There was this possibility to apply for Helmholtz Young Investigator Group on AI and energy, because I'm from the energy background, also from the Helmholtz background of KIT. And then, yes, I said, okay, cool idea. And all I did was somehow mentoring you a little bit, but most of the job he did by himself, and he simply won this Helmholtz Young Investigator Group, for which you have to pass a really hard test in Berlin. So everybody in the room who thinks that it's easy to win a Helmholtz Young Investor Group, Achim is also giving the right sign. No, it's not at all easy, and he did it, and he won it, and we were really glad. Yeah, and so that was first touch, and then you've been in Norway, yeah, and it was clear you will come. And at the same time, we had by the Haiku, which is also a Helmholtz initiative, there was, yes, a tenure track professorship for energy and AI. Yeah, and someone who wins a Helmholtz Young Investigator Group has evidently a very, 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 very brilliant CV. So no wonder he also won that tenure track professorship then, and that's why he's here. Yeah. So to come to conclusion now, there was some biblical terms. Now perhaps I should also sing that he's here, hallelujah, revelation and glory, or something like that. I'm tempted to take your name because Benjamin in the medieval times was known as the great, by Richard of St. Victor, for instance, as the great mystic. And me personally, for me, all of this artificial intelligence, which was a counter notion against cybernetics historically, perhaps you know that, because it was they in that Dartmouth College 1956 or something like that. Yeah, so they wanted to have something which is purely on data and not as this cybernetics. Let's say science founded by Norbert Wiener, who was on modeling, also on physical models. They really wanted to have a counter argument. And my basic formation is cybernetics, yeah, from University of Stuttgart. So, and still, I don't know what this artificial intelligence, which in English simply also means to treat data intelligently, yeah, what that's all about. So now I take that mystics, people of the medieval times, and like say, perhaps you can shed some mystical, clarifying light on artificial intelligence, and hopefully it will help us all for building up the new energy system design, because by Per Nowack, you said we have to do something, yeah, and we have to do it rapidly. So I hand over to Benjamin.
Thanks a lot, Veit. That was great. And also as maybe some background, I think this idea of you singing was originally suggested by an AI because we asked Blablador, which is like an open LLM hosted at Forschungszentrum Jülich, Research Center Jülich, what it can tell us about Veit Hagenmeyer. And it told us that he actually landed some hits in the German song, I don't know, ranking. Yeah, I think something like this. But you also verfeulte the top, whatever this, I didn't know this German word, so Blablador also invented some new words. So I'm also going to switch. Okay, so great. So this is now the talk on AI for energy systems, right? So we just heard from Per that obviously climate change is happening, temperatures are increasing, and the question is, what can we do about it? And one of the main ways of mitigating climate change is going for a sustainable energy system. And I also should say, jumping right into the topic, that I'm also really pleased to see so many people here. And I think I'm just like Per, like, okay, I know a lot of people, but I also don't know everyone. So it's like great to have this opportunity to present us and myself in this case. Yeah, so really nice that all of you are here, both the new and familiar faces. So I wanted to talk about briefly where I come from. And so I was born in a different country than Per. So I mean, Per was born like somewhere there, right? I was born actually in like around there, which was still the GDR when I was born there. So like East Germany. But barely. So I also studied close to this because my parents told me, you want to study in Munich? No way, we can't afford that. So yeah, I studied a bit more locally. Had my stop in Göttingen for a PhD, which was really nice at the Max Planck Institute. And then actually during that PhD time, I also went to London and then to these islands there, which are also like, as everyone knows, northwest of London or England, where Japan, in Tokyo. I also had a very pleasant stay there, and then had like these postdoc positions at Dresden, and then a Marie Curie fellowship in London. So always had this impression of like self-finance, because I first had a stipend which I won. Then so I did get employed on a third-party grant for the postdoc fellowship, but then the Marie Curie fellowship and now the Young Investigator Group. So always had a bit of a feeling of an uphill battle, which might relate kind of to this East German history. So kind of a narrative there, I felt. Then I was briefly an associate professor in Oz at NMBU, and I actually made this very weird decision to quit from a permanent academic position, because there I had my own position. full stop, unfortunately. So if you don't know where Ås is, it's actually very close to Oslo. It's kind of the agrarian university of Norway. So it has quite a long, nice history, 5,000 students, a beautiful campus. So if you ever want to visit someone with a very nice campus, I recommend to go there in June. In July, everyone is on break because it's Norway. Like everything's closed, kindergarten, schools, like no one works. But if you want to go there in June, like it's a very nice place, or in August, also a very nice place. So then, yeah, as Veit already said, right, I started my Helmholtz Young Investigator group at KIT at Campus North, AI, and since last year, May, and I made it just barely before I'm a professor since more than a year to also have this inaugural lecture, right? So check. I was much faster than a lot of my colleagues now. So that is nice. Okay, so maybe also to give a bit of background and where this comes from, Veit already mentioned this, that there was this HAICU, Helmholtz AI Cooperation Unit, and this, I think, is a very cool thing, and maybe also from kind of Helmholtz perspective, Campus North perspective, something really cool for maybe many of you. Oh, sorry. So the idea is there's a kind of central hub in Munich, which isn't super important, but there are like research units. Sorry, it's not super important for us. Yeah, sorry. Okay, this is now on tape, right? It's super important. Everyone doing their great science and a great job. Okay. For the purpose of this talk, they are mostly concerned with the health research field. And then there was this competition more or less to attribute these different research fields that Helmholtz works on to different places, and KIT ended up winning this energy local unit, and the local unit consists of a consultant and of a research group, and in our case this is Markus Götz at SCC, and he is kind of the person institutionalized where people can put vouchers to and ask, like, I don't know about this AI thing, can you help me, right? And this is kind of their job. And I see like some faces from Markus' team as well. So if you're interested in that, this is like a nice service. If you still didn't do a lot of AI stuff. And then we have these research groups that are kind of closer to the domain, closer a bit more to the method development in terms of how it's set up. And also part of the Helmholtz AI is like HiCore, in addition to Horeca, actually, and also Helmholtz AI grants. So there's actually also some money out, which now is getting more competitive to win, but there are actually some nice projects, or you can become an associate of Helmholtz AI if you're ever interested in something like this. So I think this is like a really cool platform to connect people from like different fields, different research areas, different Helmholtz centers as well. Okay, so I traveled a lot. So this is the group I already assembled in the last year and a bit. And I called it like data-driven analysis of complex systems, and kind of the mission is to use data to understand complex power systems. And I'm actually really pleased that the team turned out so international and interdisciplinary as it is, right? So I listed some of the things, and we are including myself at a 50% female rate, which is much higher than the kind of typical computer science students in Karlsruhe at the moment, unfortunately. This also, I guess, goes hand in hand with the high international degree, right? So yeah, thank you. Yeah, I want to push also for, like, I mean, I'm a German white male guy, so I think it's important to still push for more diversity, to have like really great creative minds come up with creative solutions to these important and difficult problems. Okay, so now let's come to a bit more science. So this is kind of the motto of the group, right? Making complex systems transparent. And this means ideally you start with some data, because it's also called data-driven. You build some models, right? Maybe you do something simple like a linear regression or a deep neural network or something more complicated, and like hybrid models or something, then you get predictions. But I really emphasize this bottom part here to also get explanations, right? So Per already mentioned this explainability aspect, and this is really important for me to not get really black boxes in the end, but get models that are explainable, where you get some insights and learn something from using them. So, I mean, I originally studied physics at some point, so this is maybe also relating to this, that I want to understand what's happening there. I think there's more of, okay, can we probe the system, understand what's happening there, down there, and how can we then, for example, control and design energy systems that are sustainable in the future. Okay, so jumping into what is happening there, right? Why do we need this? Right. So this is a sketch of kind of the past energy system and the future energy system. So obviously we learned climate is warming. So one way of limiting this is let's not burn any fossil fuels anymore. And let's not emit any CO2, which means we need renewable energy like solar, wind, hydropower. If you want to include this, nuclear power, then political discussion in Germany. So maybe a bit sensitive, but most of this will lead from central to decentral. Nuclear power is kind of out of this, but you can build like large nuclear power plants. But most of these like volatile, especially wind, solar, are typically decentral. We have an increasing number of actors, right? So you have maybe your small power plant at your balcony on your roof. You have lots of consumers that also might have a more active role. This is also represented down here. So maybe the consumers are no longer consumers that just consume downstream, but actually might have a bidirectional exchange because they are at some point exporting power from their house if they're not at home, but there's lots of sun during the maybe noon time. They actually might be generators, right? So-called prosumers, consumer and producer combined. And another important thing is that, and I think that, for example, connecting to Pascal Friedrich, is like this idea of AI for maybe material science. We also have like lots of materials and technologies in the energy system. New batteries, new PV modules, stuff like this. And also, quite critically, we have more data. Right? So we have more smart meters in Norway and the UK, where I live, for example. It was much more common to actually have a smart meter at your home to monitor your consumption and get maybe even independent tariffs for your consumption, or weather data, also in experiments. Okay, so large amounts of data also include transparency platforms, which is in this case from the ENSOE, a large European organization. And you can, for example, look up, okay, what was actually generated in terms of biomass during short time windows. For a recent application, which turned out to be not successful, we estimated some of the data we could pour into these models. And just on these transparency platforms, you get something like 500 gigabytes. Some of the Helmholtz data treasure Veit already teased, including, for example, this electrical data decoder, it's like another few hundred gigabytes, and then maybe auxiliary data. So we already estimated that even if we just look at time series, right? This is not images. Obviously, images will have like much larger amounts of data typically, but just time series on a reasonable resolution, right? So we record, like the original recording is maybe 20,000, 30,000 measurements per second. But this is not an interesting signal, right? There's lots of small fluctuations in there, but this is something like second scale to minute scale time series, which actually carry meaning. And there we are definitely in the order of a GPT-3 kind of model in terms of what we could train there. So maybe we go for like some foundation-like model for energy systems at some point. Unfortunately, a recent application didn't turn out, but yeah, let's still stick to something like this. Okay, so now we have data, but what can we do in terms of AI? Right? So maybe like one general thing I would say is like the core challenge in the energy system is actually balance. Right? So what you want to balance is generation on the one hand side and demand on the other side. So if those two are in balance, everything's fine. And almost everything here then relates to keeping this balance on timescales of seconds, sub-seconds, but also up to minutes, hours, years, decades potentially. So you have like generation on the top level, transmission, and then consumption. And actually, interestingly enough, that on all of those different things, there are already some publications. Like this is on the more material science idea, again from like vouchers from Markus' team. This is something Ralf Mikko at our institute started, like more forecasting on the consumption side, for example, but also what we started with Sebastian, who's also here. One of my earliest PhD students was quantifying regulations and their impact in transmission systems and electricity prices, for example. So most of this is going to be a very short teaser. So just to give you an idea of one of the main quantities we're looking at is this frequency stability. So I told you balance is like the critical thing. And at the moment we are running an AC system, alternating current, which means we have in Europe a 50 hertz, in the US, for example, 60 hertz, in Japan, both signal. And this will just tell us how balanced the system is. And yeah. So just to give you an idea, so when we had the Neckar West power plant, which was a bit more than 1 gigawatt, this actually deviates to 50 millihertz, or translates to 50 millihertz deviation. So even if we talk about like small numbers, millihertz and so on, actually this is a lot of power, because a nuclear power plant intrinsically feels like a lot of power going on there, right? You don't just switch on or off a nuclear power plant within seconds, but actually these frequency deviations happen within seconds or shorter times even. So if we're talking about something like 200 millihertz deviation, we're talking about several blocks of a nuclear power plant. Right? And you can roughly think about this as a turbine rotating 50 times a second. And now you need more energy in the system, so you slow down the turbine to satisfy your additional demand. Right? So, and vice versa, if you feed more in the system, it speeds up. It's a very, very simplistic picture of this. And actually getting data wasn't so simple, right? So this is a story from 2016 during my PhD. So what I did is I naively contacted a couple of companies and no reply. I was in Japan, in Tokyo, so I asked also my host there, okay, who could I contact and how do I get more data? And what happened is actually I received a 5-page 12-screenshot instruction of how to download data. I think Google Translate wasn't great at that time, but with Japanese, my Japanese was horrible. I could just barely say hi and I want this. So this was like very helpful, right? Click here, click there, of like downloading it. I checked it, it still works. But now also Google Translate could have told me this, I think. But overall, this isn't really fair, right? It wasn't something that was findable or accessible in any way because I needed like specific Japanese instructions to follow to actually download any data. So this is when this idea really came into fruition to work with people from IAI, and I put a few pictures here. Who constructed this electrical data recorder, which you use to locally record the frequency. But actually now we distributed this a bit around the world already, or we started doing this. So we take this, for example, on conferences. This was when I was in Florida last year for an ACM conference. And we already sent some devices to some colleagues. And there's like some backend that this uses, for example, connection to a satellite to synchronize the clock. And then in the end, also on the networking and storage side, this is sent to the large data storage facility on the SCC side before it's then again processed back to us to use like from this 30,000 measurements per second to something more interpretable, more relevant, let's say, on a 1-second time scale. Okay, so what I thought is let's actually advocate more open data usage in this community, because obviously there is a lot of data known in power systems, for example. The companies, they collect data, but typically they just sit on the data, right? So Iceland, for example, they told me, yeah, we only share data with an NDA, but Iceland is isolated, right? It's not like there are other competitors on the same grid. Also, like in Germany, when you talk to people like Transnet, for example, who was responsible for the Baden-Württemberg power grid, they have data for power plants here, but they don't share all this data with, for example, TenneT, a neighboring transmission system operator, and vice versa, right? So they have to share something, but they actually don't share a lot voluntarily. So what I thought is, okay, maybe also other researchers have data, so let's try to be a role model and publish more data, right? So we had this idea of record some data, publish data using FAIR, and then we did this in 2020, for example. We had this web page, which is currently undergoing an overhaul because we wanted to do this a bit more scalable, more automatic. I think we don't really use AI for that, but maybe AI downstream applications then. Okay, so another important point for me is this XAI, explainable AI. And I really like these comics from Molnar's book about, okay, so you ask a computer, your model outputs something, and then it tells you 42. And then you're like, yes, great prediction. So it's going to be 42 kilowatts or something. And now, right? The question then is, okay, do I trust this prediction, for example? What do I do with this prediction? Where did it come from, and so on, right? So again, a bit of a physicist's view is, in the end, I want to understand the world, and ideally we capture it in data, we build some models that might have to be black box models based on the technology we currently have available, like, for example, temporal fusion transformers, and then using interpretability methods to inform any human decisions. I think this is particularly critical for power systems because it's like critical infrastructure. We don't want to have a blackout. So what we need is people to really trust what's happening in these models, to either have the model like proof by design more or less, or or we have to make sure that they actually understand what's happening there, and that if a decision, for example, from the model tells them, like an operator, do this or that, they can ask why, and hopefully get explanations they can then follow and trust. Okay, and now we ran this on a couple of things. For example, on indicators of the stability of the power system, where like there's a black box model, and then we ran some explainability, in this case, SHAP, to identify drivers and risks of the stability, right? To say, for example, okay, certain ramps in load or in generation cause certain risks. These certain generation types don't work well with each other. So we tuned this down, the statement, because it turned out that nuclear and solar don't work that well together. And we felt like this is maybe a bit sketchy if like people tell us, okay, but this is very dogmatic. So we said there are correlations, and we are also working to include more causal structuring in these models. I think this is an important extension that needs to be done. You can also run this like on electricity prices if you're interested in that. And like to tease one thing that was at work early last year was to look into like power systems that are governed by regulations, right? So maybe as an operator, or sorry, as a regulator, like Parliament or something, you have an idea. I want to change the system from that state to this state. And what we ask is, okay, we have a before and after. In this case, we had like 2 electricity prices. And what happened is the Austrian electricity grid at its own price after a certain period here. And we trained like models on this and asked, okay, how important is like Austria in the model? And it turned out to be not really important before the change and a bit more important after the change. Like the most important thing is still Germany, because it's the big neighbor who's like importing, exporting, buying electricity and so on. So yeah, I guess you can still say, okay, you see, for example, something like these machine learning models, they differ. You can say, okay, there are some changes. You can maybe try to analyze them, understand their impact, quantify to some extent, to say, okay, what was this regulatory change, for example, achieving what I wanted it to achieve? Okay, so I'm also getting quite over time, so let me just see some of the things. What we are now also working on is something like identifying complex dynamics just from data, right? So given some data, can we get the governing equation? So ideally some ordinary differential equation or stochastic differential equation description just from data, right? So you put in some data and ideally you simulate something that is very close to the original dynamics we extracted. And this is actually wrong. This is no longer ACME energy. I'll review it as ACME energy accepted, and also at the ICLR workshop on climate change impact this year. So that's quite nice. Quite proud that this worked out. Okay, and we produce like key characteristics. I think we convinced like some of the reviewers that this actually works. Okay, and another interesting thing is if you're talking about forecasting, a lot of the forecasting I see in power systems is actually on a very coarse scale. So maybe minutes, 15 minutes time resolution. And then if you want to forecast a day, it becomes quite easy because it's like 24 hours times maybe 4 because you have like 4 measurements per hour. But if we have like 1 second time resolution, this actually turns out to be like much more data, much more highly resolved. And we ask questions, is this working? And again, it tends to work. Otherwise, it wouldn't be here. But physics informed is also like a very important point because we know some of the underlying mechanisms in these power systems, right? It's not like we have to invent everything from scratch, but we know that some of the systems, for example, are controlled in a certain manner. And we can include this control in the modeling and estimate, for example, parameters from the data. Right, so we can formulate, for example, a stochastic differential equation and then estimate parameters using a neural network, including some external features, something again like load, generation, prices, stuff like this. So all of the information we have. This is kind of for transmission systems, a large scale system, but you can also think of this as maybe if you're living in a house, maybe I know, okay, how's the house built, how many people live in there, what are their habits, right? I could also include these kind of features instead. Okay, so on reinforcement learning, this is actually a kind of recent project we started last year. So we don't have huge results yet to show, but obviously if you have something that needs controlling, I felt like from the machine learning side, reinforcement learning is like the natural choice to go to. And there are like very nice rule-based control mechanisms in power systems, but they don't necessarily utilize all the data that is available. And they also need to be very fast, right? All of these decisions need to be fast. So the question is, can we use reinforcement learning to optimize, for example, in this case, a local setting, or can we use it to run a power grid that also needs to be stabilized all the time more efficiently? Right, and this is the question is, for example, how does this differ from maybe model predictive control algorithms? What can we learn again for maybe then designing a better model predictive control that is maybe more accepted in the community, but maybe the machine learning tells us, I do this, and you're like, okay, this is like similar to, let's say, the AlphaGo. The player said the machine did moves that no human player would have considered. And this is kind of the idea here. Get inspired a bit by like a completely unbiased individual, effectively. But then again, you need explainable AI to actually understand what's happening there. Okay. So with this, I would kind of close with a brief outlook that some of the things can be actually really, so this is, I think, a value for being at KIT, can be implemented, tested, or utilized data from the Energy Lab 2.0. So for any of you who haven't been at Campus North yet, this is actually like a really cool research facility. Our institute also has an internship practicum for all the students, if they're interested in that. You can do like research topics there on a small scale within a few weeks. So this is like really cool to use for monitoring. There's more and more data being collected, actually. And also the idea, for example, for reinforcement learning is that there are individual houses, and for the houses, we can remotely control the windows, we can remotely control the heating, the electricity, and so on. So I think this is like a really cool test bed to actually see, do these agents work? And then in terms of explainability, for example, this is maybe getting kind of stretching a hand out to the robotics community here as well. How do you like make people who then interact with these like machine agents actually accept this in a way, right? So why is my window opening? Ideally, you have a good explanation for that, and then people hopefully accept such solutions as well. Okay, so in terms of teaching, I also already offered like pro seminar and seminars last winter term, and this summer it's actually been a lot of work. I prepared the lecture Data Science and AI for Energy Systems. It's kind of in the energy informatics subject area, let's say, which Veit started here, I think, or continued at least. So the plan currently is also to go for the Grundlagen der künstlichen Intelligenz, so basics on AI, in this winter term. And actually, we have a growing number of student theses in the group, which surprised me that at some point so many people contacted me. But it's quite cool to work with so many people here and get a very diverse sampling. And everyone was quite excited on this topic. So with that, let's wrap up. Right, so I talked about like large amounts of data available and complex problems in power systems that hopefully you use explainable AI for to understand a bit better and to get solutions that do get accepted in the engineering community. And then applications in this whole area range from stability, prices, maybe investigating laws, regulatory changes. So I would say it's quite an exciting field, and I would just second what Per said. So I think it's a really exciting field, and if you're interested, feel free to reach out. I'm happy to collaborate as well.
Yeah. Another very interesting talk, and also another very interesting topic. I'm wondering if you couple both approaches, if we can solve the problem of climate change finally. Okay. Thanks a lot, Benjamin. Thanks a lot, Per, for giving the talk. Also, thanks a lot for the introductions. It's now the time for drinks. Exactly.
So if I may,
yeah,
we just have a very brief thank you slide as well before we go for drinks.
Okay.
Right? So we just wanted to, like, both of us actually thank like the whole department or Fakultät for actually having us and hiring us and supporting us all the way here. Also our institutes, like at Campus North, the Großforschungsinstitute. Also to you, to Peter and to Veit for having such nice words of us. And also a rap. I wasn't expecting that. Thank you. Made my day. Also to Marina, Astrid Hopprich, Isabel Häuser, Thomas Griesbaum, and everyone actually who supported like this event or us in general. For all of you for coming. And this is what happened when I asked Stable Diffusion for like some thank you and have some drinks and pretzels. You can see that sometimes the pretzels aren't super nice, but with that I would actually second what Michael said and just say, let's have some drinks and snacks.